Greetings, Earth enthusiasts. If you ever wondered about the incredible perspectives our planet has to offer from high above, you're in the right place. I am Dr. Clive Coetzee, and I'm thrilled to be your guide on this captivating journey into the world of remote sensing. Welcome. And please remember to like, subscribe to, and share this video. Thank you. So we picked up on our urban heat map or urban hotspot or urban heat island journey. In our previous video, this one here, 162, where we last ended, or we just continued with this. And 162 is sort of just looking back at what we've done, like a summary of the work that we've done on this particular item. So we're going to continue with this in this video, and hopefully we at the end of this video we'll have our urban heat map, or we'll have our urban hotspot. Boys and girls, again, just please a reminder before we continue, please like, subscribe, share this video. Please feel to comment on it. I thoroughly enjoy your comments. Yeah, please, let's get that numbers up. I think over 70% of all viewers are not subscribers. So if all 70% of you can press that button, then I'll get to my numbers. We'll get there. So let's grow the channel together. I really appreciate your support. Okay, so remember in the previous video tutorial, this 162, we basically ended with our average or our median land surface temperature image for our region of interest. And this was for 2023 winter. 2023. Okay, so now we've got our land surface temperature. Again, this is a mean temperature. You can work with median temperature, that's up to you. Okay, so there it sits, our mean land surface temperature from our MODIS data set as per its landing page. Okay, we've got this. Remember, what does the theory, what does the idea behind this? It says that urban areas, concrete, absorbed, keep heat much longer, much higher than vegetation. Vegetation, non-urban areas, non-concrete, reflects a lot of heat. Remember, for example, between a white car and a black car, that a black car, is it the black or the white one? Which is cooler? I can't remember now. But anyway, one is cooler than the other, and that's because of the absorption or the reflection of heat. I think it's white. White reflects heat more than black car, so a black car would be more warmer than a white car, or something to that. But I hope you get the idea. And that's sort of the idea behind this, is that urban structures with lots of concrete and things like this will absorb heat, will have higher land surface temperatures than the neighboring area. And so this is our mean land surface temperature for our region of interest for 2023 for this particular period. Okay, so what happens now next? Okay, now okay, so once we've got this, the next thing is to generate what we call a urban thermal field variation index. Okay, that's a hell of a long word. I'm gonna struggle to remember that one. It's urban thermal field variation index. I hope you guys can pronounce it. Try that when you're not sober. Huh? Nonetheless, that's just joke, tongue in cheek. Huh? So nonetheless, we're going to generate this. Okay, so what is our formula for that? So UTIFV is just an abbreviation, obviously, of this thing. This urban thermal field variation index. So what we have is, and I'm using my median images. You can use a mean image. So let's say this is our, okay, so we can generate the mean image as well, but I like to use my median ones. Now, okay, so before that, sorry, I skipped one thing. Before that, we have to calculate the average land surface temperature for my whole region of interest, and I've also calculated my median land surface temperature
value for my whole region of interest. Okay, so this is what we've done here. Okay, so calculate the average land surface for my region of interest. I've got my modus mean. So this is my mean image. Okay, which is this one here, my mean image. Okay, so call it the mean of a mean. So I'm taking my mean image and I'm calculating the mean statistic for my whole region of interest. Okay, so I'm calculating my mean land surface temperature for the whole region of interest. So that's what we're doing there, and I'm just printing it. Okay, and that is what I'm calculating, the average land surface temperature from my mean image. Okay, and there it is. Okay, and we print it, and there it sits. So that says it's 20.58 degrees Celsius. So remember, that's the mean for this whole area, not for a particular area. Because remember, what we want to get is we're saying that that should be the temperature, and everything higher than that thereby is urban areas. We've done the same for median as well. So there's my formula or my script to calculate the median image. So I'm taking my median image. Okay, so I'm not taking my mean image, I'm taking my median image. This one here. Okay, so I'm taking that. And where is it now? Yeah, and then I'm using the median reducer. Okay, and I'm displaying that. So now I have a median um, number as well. And there it is. So my mean is much more than my median. Now that already tells you quite a lot of interesting things, okay? Because that means there's positive outliers. There's a few locations with high temperatures, and most of the smaller temperatures are clustered around the lower end. So if you a little bit of statistics, if your mean is higher than your median, then it's positively skewed, meaning we have a few high numbers and a large amount of small numbers, because the large amount of small numbers is pulling the median towards it, whereas the few large number is pulling the mean towards it. So that already tells you there's a couple of places within the city that has exceptionally high temperatures, where most of the areas have low temperatures. So that by itself indicates the presence of urban areas or concrete or places that absorbs a lot of heat, because the area by itself is not sufficiently large that the temperature by itself will have different the temperature by itself is different, if you understand what I'm saying, meaning Cape Town by itself will have one maximum temperature or one temperature for the whole area. It's not a country where you have different temperatures because of it's so far from one another. Cape Town is a small, dense area. So the land surface, the difference in land surface temperature is not because of the difference of temperature. It's a difference of the location. I hope that makes sense. I'm trying my best to explain that. But that's the case. So the just the mere fact that the median and the mean are different, and that the median is more than the mean already tells you something. Also understanding that we're working with surface temperatures, not air temperatures. As I said, the air temperature most probably will be same for the whole of City of Cape Town, because it's such a small area. So the difference is not because of the air surface or the air temperature, it's because of what is on the surface. That's what the difference is. Okay, so this dynamic is already quite interesting by itself. Okay, so what we're saying is we're going to use this now as our average temperature for the whole region of interest, and then we're going to identify areas that's above it, and we will say those areas that's above it is typically areas that would absorb, hold, keep a lot of lot of heat, and that typically would then be our urban areas. The areas below that typically reflect a lot of heat, would not hold a lot of heat, and that typically would be vegetation and things like this, i.e. non-urban area. So that is the idea behind this. Okay, so before we do the thermal invariance, thermal field variance index, it's important for us to calculate that statistic for our region of interest, because we're going to take each pixel and compare it to that. And that's exactly what we're doing in terms of this. And here I'm working with my median numbers, okay? Median numbers, not the mean. And again, that's my personal preference. You can use any of the numbers that you would like to use. Okay, that's up to you. This is my personal preference. I don't think it's going to be massively different because you can see the differences between the two are not huge. So I don't think it's ultimately going to make a big effect, but um, I don't have any evidence to support that, so be my guest and go and do it. Go and have a look. But I think the biggest change will obviously be if in the seasons. That's going to obviously make the biggest change. Anyway, so there we have, and maybe we're going to do the mean and the seasons a bit later to see what how that affects this urban heat maps or urban heat spots. Urban heat islands. That's the fancy name, I would think. Okay, so we're going to take our median image. Okay. Oh, this is this median image or mean image, either one. And then we're going to subtract each of these locations or each of these pixels. We're going to subtract it by that singular value, that 20.109, because that's what that means. That's the mean land surface temperature, which is this one, the median. So we're going to take each of these ones, whatever the numbers are, the values of that is. Okay, each of these ones, each pixel value, let's be correct now, let's not be slang. So each pixel value within our median image, we're going to take and we're going to subtract this number, the median number, which is the mean for all of them, and then we're going to divide it by the same number. We're going to divide it by the same number. So that equation yields then this urban thermal field variation index. Okay, so think about it. If there's a pixel and let's say it has a temperature of 25, then we're going to take that land surface temperature of that pixel, i.e. 25. We're going to subtract it with this value, 20, let's call it 20, just for rounding. So we're going to take the 25, we're going to subtract it by 20, that gives us 5. Then we're going to take that 5 and we're going to divide it by the 20. And that should give us, what is 5 divided by 20? Let me quickly just go to my cell phone and say, what's it, 0.4, calculator, 5 divided by 20, that's 0.25. So that will, for that pixel, will then yield a value of 0.25 and so forth. Okay, so that's what we do there. We calculate that urban thermal field variation index, and there's our parameters, our visualization parameters, etc. Meaning green is minus 0.03 or on the lower end, and red is on the higher end. Again, do the calculations, understand the formula, and you'll understand the higher that value is, the more that pixel value is above the median value. The smaller it is, or negative it is below that value. So high values to this side would be a value much higher than the 20. Low values of values to that would be lower than this. Okay, I hope that understands. We have our visualization parameters, and when we're just going to visualize it, then we're just going to visualize it. So that's what we've done here. Okay, so let's have a look and see what that looks like. And there it sits. Okay, there it sits. It's just starting to load there, and voila, that is our so-called urban thermal field variation index. Okay, red is much higher than 20, green is much lower than 20. So that already gives you an indication of these locations which attract, absorb heat versus those areas that reflect heat, meaning, i.e., build-up areas versus non-build-up areas. And let's have a look at it. So we're going to use our inspector. Let's click on a red area. And let's go and do the calculation. So I'm not going to go that one. You see, so that is for that specific area that I've pressed, that is its median land surface temperature, 23.4. So we take that 23, then we're going to subtract it by 20. That gives us 3. And then we're going to divide it by 20. And that should then give us a value of 0.167. So remember, what did we say? We can actually go and check it. So let me go back to the cell phone. So we're going to say it's the median temperature, which is 23.45. So it's 23.45 minus the median for the whole region of interest, which is 20.09. So I'm just rounding. And then I'm going to divide it by 20.09. And what do I get? 0.16. What do we get here? 0.16. Yep, there we go. Voila. And you can do the same for the green. So in the green would be the value of that region of or that location would be less or very close to 20. And there we go. It's less. 20.8 versus 20.09. So it's just above it. So it's going to be, yeah, there we go. It's going to be very, very small. Okay, so that's basically how we calculate the urban thermal field variation index. And that already to a large degree overlays with our urban areas. So if let's quickly put it on satellite again. And then if I increase the transparency, let me take away that. You can see there. That's obviously the urban areas here. Let's take that away. You can see that's urban area here. You can definitely see it's built up. Okay, so let's do that again. You can see it overlays almost perfect. There's some areas here. Okay, let's make it bigger. Let's make it bigger. You can see this is all built up areas, né? All built up areas. So let's go to the thermal thingamajig. Okay. Takes a bit of time, but you can see it basically covers. Okay, the pixel sizes are a bit of a problem. That's why you have these overlays. It's because of pixel sizes. Let's have a look here. Again, the problem being bare soils. You can see there some bare soils here. It's picking up bare soils. Obviously, there's also some bare soils. Okay, that's Alentis Industria. So that's industrial. That's bare soils there. We're not going to get rid of this bare soil thing. Now, that's the problem. Because bare soils also attracts a lot of heat, keeps a lot of heat. You try walking on sand when it's hot. Your feet burns like hell. So, well, you can do the exercise yourself. There's a rugby field or soccer field of grass. Walk on the grass in the summer, then walk on the sand or on pavement, and you'll quickly see the difference. And that's exactly what we're trying to do here. So it does suggest that. Yeah, so overlay, it identifies these urban areas. Not perfect, not 100%, but it's a good, it gives you a good indication. Like there's something there. Go and have a look. There's something there. Okay, so that is what we call the urban, the urban thermal field variation index. Okay. We're just creating a histogram of our temperatures. We just do a histogram of it. It's not really an issue for our median. Just a histogram, you can see a lot of, remember that's the median is roughly here. You can see a lot of small numbers, very few high numbers, and that's why it's positively skewed. So that's just confirming the difference between these two, or the layout of the data, so to speak. Okay, so that's just for interest. Okay, so now once we've calculated our urban thermal field variation index, I can't even pronounce the abbreviation. So let's go just thermal index for short. Okay, so when I talk about the thermal index, just take note that this is for this whole long thing. Okay, next thing that we have to do is we're going to do the standard deviation of the land surface temperature. Calculate the standard deviation of the land surface temperature. Not using this thermal index, we're going to use land surface temperature. We're going to calculate the standard deviation. Okay, so it's take our data set, which is, let's go back to our data set. Where's our data set? Let me just go, there's our data set, okay, which is basically just this thing here. Okay, so that's our data set, process modus. So that's our raw image. So where are we now? Calculate, sorry, I keep on losing my place. So we take our raw data set, we reduce it by the standard deviation. And that would be then our band, and we clip it for a region of interest. So this is a new image that we create. Okay, this is not reduced by median. It's not reduced by mean. It's reduced by standard deviation. It's just presented in a different way, but it's basically the same format as this, except this we will just say standard deviation. So it's exactly the same as this because we're up to this. So all we do is we take this whole thing and here we just change to standard deviation. So that's all we do. It's a new image, but it's based on a standard deviation reducer. Okay, so that's what we're doing there. We give it a name and we clip it. Okay, hope that makes sense. So let's go back. You'll see in here, where is it now? There's, yeah, so we just up to there is exactly the same. And then we just give it a name. Let's go back. There we go. So that's what we're doing there. And then there's our standard deviation visualization parameters. Again, 1 to 5. Now, again, you need to understand standard deviation. Standard deviation is just the difference from either your mean value or your median value. And one would assume that one standard deviation is within 99%, two standard deviations within 90%, etc., etc., etc. So 1 means it's very close to the mean. 5 means it's quite far from the mean if we use our mean. Anyway, yeah, so we used the data set, the normal values. Yeah, so it would be, remember we use, yeah, so it's a standard deviation. So it takes all these images and calculate the standard deviation of these images. Okay, so that is it. So let's see how that looks like. So we display that. Okay, so let's have a look, see what that looks like. That's our standard deviation. Okay, so that's our standard deviation. You can see the red and the greens. Okay, so let's quickly click on the red and see what that says. So it says that, okay, so let's have a look again. So there you can see the thermal index 0.4 because the median value is way above the 20 value. So that means it's hot. So it has a standard deviation of 4, which is, if you look at the color scheme, which 4 lies to this end. So it deviates quite a lot off the mean. So that means it's much higher than what is expected. Okay, so if so it's much further away from that 20. Okay, so let's go and have a look and see what is blue. So let's go and have a look at blue. So let's have a look at blue. It should be, you see standard deviation is 2, which is closer to the 1. So that means it's closer to that 20 value. I hope that makes sense. So the higher the standard deviation is, how further it's higher it is. Let me put it this way. The higher the standard deviation is, the further it is from the 20, i.e. the hotter it is. In a nutshell, in plain language. Okay, so I hope that makes sense. Okay. Okay, so that's what we've done there. Okay, we've done the standard deviation. And we've added the standard deviation to our maps. And then we say we calculate the area with high UTI value. Now here we're saying if it's greater than 0.06, then we only display that values, and we display it as a red. And that would be this one here. Okay, so here we're only displaying the values, and that's our value there. Now again, that's up to you to decide what that threshold is. That's our threshold value. Okay, that's our threshold value. And we just display that threshold. So we're saying within this index here, this index that we've calculated, this, where's that fancy word? Thermal, urban thermal, blah, 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 blah. Urban thermal field variance, that UTI VE. So only display UTI greater than 6, and then obviously mask the values that's not. And you can change this value. You can make it higher. You can make it lower. That's trial and error to a large degree. Okay, that's trial and error to a large degree. So we're displaying it, we're adding it, and then there's some statistics that we're going to calculate. That's our land time series. That's not the reason for it. And then we're going to identify hotspots, which is the same. We use that, etc., etc. So the hotspot is the same as the high UTVI areas. Because we do the same thing, we just use different. You see here we have 0.006, and here we have 0.05, and we just do the same. We just say it's hotspot, but it's basically the same thing. Hotspots, UTIV8 greater than 0.05, and here we have high UTI values or heat maps UTI greater than 0.006. And yeah, 0.006. That's quite a 0.006 to 0.05, and the difference. Let's have a look at the difference between the two. So that's hotspots. That's just what I want to see. That's much more than. Okay, that's high UTIV areas, and that's hotspots. So the hotspots is much less because our mask is much higher, and that seems more accurate. There's still a bit of sand here, much more accurate. And that's basically it, boys and girls. There we've calculated. And there's some other things that we just add a legend, which is this one here, blah, 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 blah. That's how we've done the legend. And so forth, and so forth. That's just to make it a little bit more pretty, but that's just academic. But that's, and then we can export it. There is our export function. So we've created a hotspot, which is on 0.05, and we have an urban heat map, which is greater than 0.006. But we can change these values. That's up to, just remember, if you change dates, you change anything, remember to take those numbers into account. And it's based on median statistics, not based on mean statistics or some statistics or min statistics. Okay, that standard deviation one that we've generated, again, that's just another image that we can use. And we can use the standard deviation image to calculate the average standard deviation. So rather than to use to calculate these ones, we can basically calculate standard deviation. So you can do this based on a standard deviation as well. So there's a different techniques to calculate these sort of things. Okay, so boys and girls, that's basically urban heat maps or urban heat islands or urban hotspots, whatever terminology you want to use or abuse, that's how we can calculate those things. So with that said, let's yeah, we're going to play around further with it. Let's see if we do change in dates. Let's do that in next week. So let's play around with this to see how sensitive this method is to changing of these variables. Okay, so that would be interesting to have a look and see, okay, how sensitive is this variables? Anyway, and that's basically that. It took about, 3 weeks to get here, which normally would have taken 2 or 3 days. But we took that detour, and now we're back. And so this is something in your toolbox to use. I think it does have merit. It seems to be able to identify urban areas fairly reasonably good. It's not perfect, but it seems to be okay. Big problem is your urban areas must have scale to it, must be large, sufficiently large enough, which is again one of those difficult ones to define, but it seems that there has to be sufficiently large enough, and it has to be the issue of bare soil is again a problem. So those two assumptions or those two constraints, make sure, and then we can apply this. So yeah, that's urban heat maps or urban heat islands or urban hotspots in a nutshell. Cool, great. So with that said, boys and girls, thanks again, and please, please, please remember to like and subscribe. It does help. It does help. It does help. So yeah, please press those buttons. Please press those buttons. Okay, and with that said, I'll see you on the other side.